In this lecture, I want to talk about stereochemistry. So just to review, stereochemistry usually occurs when a carbon has 4 different groups attached to it. It's not really a definition of stereochemistry, but it's a good starting point. So it usually arises when a carbon atom has 4 different things attached to it. And so that is a good starting point. Now, so let's draw a carbon, and we're going to draw it as a tetrahedral center. So we'll have a wedge coming out at us, a dash going back into the board, and then let's just have 4 generic groups that are all different. And I like to reserve C for carbon, if I can. What I'm going to do is consider a mirror plane. And by considering a mirror plane, I'm saying let's draw the mirror reflection of what we've just drawn. So C is still C, going up is still A. Now going down into the right is B, according to the mirror. D is still coming out at us. It's just moving down into the left this time. And then E is going back into the paper still, just down into the left also. Okay, so what we have to make note of here is that when we consider this mirror plane, the mirror image of a C atom, how about this, of a molecule with a C atom, with 4 different groups attached is not superimposable on its mirror image. So it's chiral. So we've shown the molecule and its mirror image, and we show that when the molecule and its mirror image are, sorry, I figured out how, there we go. We show that the molecule and its mirror plane and its mirror image are not superimposable. We say that the molecule itself is chiral. Now, what I'm going to do is something, I'm going to be kind of proud of myself here. So if the mirror image is not superimposable, the molecule is chiral. That's kind of the big takeaway from chirality, is that it's 4 different things attached to carbon is really helpful, and it's a nice shortcut. But the critical thing is that when that carbon has is not superimposable, I should include this, on its mirror image, the molecule is chiral. That's the critical piece, not so much the 4 different things attached to it, although the 4 different things can be super helpful. What we say is that this is a source of asymmetry. Is a source, or maybe a property emergent to something that is not symmetric. So asymmetry is a really interesting word, and we say that asymmetric carbons are the same. It's about to write synonymous. Let's just write same as chiral carbons, which is the same as a stereocenter. So we have these sort of terms coming out. Asymmetry is one I don't use too much in organic 1 and 2, but asymmetry refers to the fact that when you have a chiral carbon, you've lost symmetry in the molecule. If you recall, when you have bilateral symmetry, we say the molecule is achiral. So asymmetry meaning not symmetry. What's interesting is that there's a lot of opportunities to discuss symmetry in molecules that don't involve anything related to mirror image chirality. And so what chemists struggle with is they need another word other than asymmetry. It's kind of funny. When they want to talk about the lack of symmetry in a molecule, it's just funny to me. You want to talk about the lack of symmetry in a molecule, which is something you'd want to do as a chemist. You would say then, oh, the molecule is asymmetric. Well, unfortunately, asymmetric implies it's chiral. There's many examples of molecules that aren't chiral that just don't have symmetry. For example, if you take a benzene ring and you have two methyl groups that are para to each other across the ring, that molecule has bilateral symmetry. You say it's symmetric. But if you put them, if you kind of put the meta, which I guess is still symmetric, if you put the meta and change one of the groups to a CF3, then it's lost that bilateral symmetry. But you can't say it's asymmetric because that implies it's chiral. Instead, you have to invent new words like unsymmetric. And then people outside of the field are like, what is unsymmetry or unsymmetric? And I don't know, it's always hilarious to kind of see the two. Anyway, asymmetry is kind of a weird word to apply to chirality, but it's what we do. Okay, so let's get back into the business at hand. What I want to do is bring about some other terms. Enantiomers. It's a term we talked a lot about in Organic Chemistry 1, and by Organic Chemistry 2, everybody could pronounce it. I'm just kidding. Okay, so anyway, enantiomer. These are molecules that are mirror image stereoisomers. Notice that I have molecules, implying we're doing a comparison of two molecules here. Okay, so if I say this molecule and this molecule are as a pair enantiomers, and maybe it's appropriate to describe them as an enantiomeric pair. Okay? Enantiomers, an enantiomeric pair. And while these don't look like mirror images, I could just flip this right one around. I'm going to do a 180 degree flip, and I would show, when I spin that around, the bromine is now facing out and it's at the third carbon from the left. Okay, so these are an enantiomeric pair. Any of these molecules or their depictions by themselves, you wouldn't say is an enantiomer. Like you wouldn't just look at one molecule and be like, that's an enantiomer. You have to say an enantiomer of what? Okay, so you have to draw some sort of comparison point. So enantiomers. Enantiomers have, or with enantiomers, all stereocenters are flipped. And flipped, or all, excuse me. All is the key word. So all stereocenters are flipped. The molecules are mirror images. And a chiral molecule can have only one enantiomer. And props to Sasha for encouraging me to figure out how to get continuous scroll. I could probably make this better by just having a bunch of blank pages. Okay, anyway, like I said, matter at hand. So the key thing with enantiomers is that all stereocenters are flipped. Additionally, if you have a chiral molecule can only have one enantiomer. Okay, so let's look at the other big word from chirality. That was diastereomer. Diastereomer, this is a relationship between molecules that are stereoisomers of each other. That means they have the same constitution, composition, and so the same atom count, the same like molecular formula, the same connectivity about all the atoms, but they're stereo isomers, so they differ in their three-dimensional arrangement. So it's another example of stereoisomers. Here, though, they are not mirror images. Okay? And what happens here is that we've flipped some, but not all, stereocenters. So this implies at least two. Why? Well, if you can flip some, but not all, like the answer, if you recall, if you flip no stereocenters, you're the same, okay? If you have the same composition, connectivity, and there's no flipping of the stereocenters, these molecules are just the same. Maybe they're conformational isomers, but that's not what we're looking at here. Okay, so we flip some, but not all. That implies that we have at least two stereocenters. So what we could have here is let's pick on this. So here we have a molecule. Let's draw some diastereomers of it. Not a mirror plane, but just some diastereomers. What we would consider is when we flip some, that is flipping either the OH or the BR, but not both. Because what happens if we flip both? We have the enantiomer. If we flip none, we have the same molecule. So I show there the enantiomer. So that's diastereomer as we have described it in organic chemistry 1. Sometimes we call diastereomers, we label them with a cis-trans relationship. And that is only most appropriate when we have rings or the stereocenters are on a ring. Okay, so an example here would be we've got this versus this. Now it turns out that I have to be careful. This molecule is achiral. Maybe I should do this. Whoop, whoop, broken the symmetry. The problem with the originally drawn molecules, I had a bilateral plane of symmetry bisecting horizontally, which destroys the symmetry in the cis isomer. Now both of these molecules are chiral. They have enantiomers, but what I have shown here are two molecules where their relationship is diastereomer. We flip some, but not all. So cis and trans isomers are often diastereomers of each other. Now, where else have we heard the term cis and trans? Well, alkenes. So alkenes can have diastereomers. Well, wait, what? They don't even have, unless it's further separated from the alkene, the carbon-carbon double bond, they don't have carbons with 4 different things attached to them, nor do they have enantiomers. Very good. These things are superimposable on their mirror image, so they're not considered chiral. But just because you're not chiral doesn't mean you can't have what are considered diastereomers. That is, things with the same composition, connectivity, but differ in the position of groups in 3 dimensions. And so sometimes these are called geometric isomers of each other. But or just labeled qualified as alkene diastereomers. But if you compare a cis and a trans alkene from one another, they are molecules. They're certainly not mirror images of each other, but they have flipped, and we haven't really flipped a wedge and a dash around, but they are stereoisomers of each other. That's for sure. So maybe alkene stereoisomer is better, but a stereoisomer that's not an enantiomer, not a mirror image, is typically called a diastereomer. So this may also apply. Okay. You know, one thing we would be remiss if we didn't at least mention in our review is that molecules, there are molecules that are not chiral, but have diastereomers and have wedges and dashes on them. So meso, these are achiral molecules that that have, let's just keep it simple, have stereocenters. They have carbons with 4 different things attached to them. It's just the hiccup here is that due to symmetry, the molecule is superimposable. So I've seen meso really throw some people off. Some of my colleagues that are instructors off their game a little bit, because it's kind of one of these weird, like, philosophical, like, is it chiral, is it not chiral, like, when does it appear? And it's just one of these things that kind of emerges. So what I have here is a molecule where you could assign R and S to either one of these carbon atoms. But in fact, if we did it, it would be R and S right here. Okay, so if we have R and S, but just because both of the big groups, the priority 1 groups at each of the chiral carbons is a bromine atom, that means we could have the opportunity for some symmetry. And symmetry destroys chirality. So I'm going to do a free rotation over the carbon-carbon single bond. I'm going to keep the left bromine the same, but the right bromine is now going to flip out in front if it was in back. And now, remembering that the Br is just a sphere, we have bilateral symmetry. If we have symmetry, we're achiral. Now, additionally, if you want to consider a mirror plane, the mirror plane, as you can see, the bromine atoms are positioned identically, and both that molecule and its mirror image are superimposable on each other. So, you know, I could even try it, right? Well, obviously, that looks, I did not draw them to scale, but so just due to symmetry, we have a meso, we have destroyed chirality. Now, what's cool about this, in my opinion, is that you start to see the physical reality of enantiomers become, and just kind of the underlying physical properties of enantiomers come to life. This molecule will not rotate plane polarized light, just emphasizing even more that chirality is really deep and built into the structure. It's not just 4 different things attached. It's all about being superimposable on that mirror image. Okay, so I think that's a good place to stop for now. In the next lecture, we're going to talk about some more advanced topics in stereochemistry. That is molecules with stereocenters that aren't defined by carbon. Okay, so I'll see you in a bit.